Welcome back, FST kiddos. So we're going to be continuing 5.8 by doing 5.8b. Today we're going to be talking about parametric equations for ellipses and not circles. And if you're not sure what an ellipse is, we will spend some time talking about the differences between the two. So our goal for this lesson is that we are going to be learning how to write parametric equations for ellipses, write both rectangular and parametric equations for ellipses, and complete problems as taught. So we'll be writing parametric equations from rectangular, and then we'll be writing rectangular from parametric, and then we'll do a graphing problem. So first, let's talk about what are the differences between a circle and an ellipse. Okay, so I have two examples here for you between a circle and an ellipse. And you can see here, we have a circle right out here. And then we have an ellipse here. Okay. So first let's look at the shapes. Okay, looking at the shapes, what do they have in common? And what's different? So hopefully you're seeing that what they have in common is that both an ellipse and a circle, there are curves that connect. So circle, we have a curve that comes back and connects. Ellipse, again, curve that comes back and connects. The main difference between the two is that this ellipse here looks like it's been kind of smushed in or squeezed in. Okay, so our circle is a perfect circle. And then we have our smooshed circle, which is pretty much our ellipse. Okay, so you can imagine taking a circle here, just like this, a perfect circle, and kind of smushing it from one side, let's say the top and the bottom, and squeezing it in. And then what's that going to do to the circle? It's going to actually squish it down where, in this case, the vertical is going to get shorter, but then the horizontal will get longer because of it. Okay, so we're essentially just squeezing it down. You can imagine me literally taking my hands and squeezing something down. You can imagine squishing a ball and seeing what happens there. So it's the same idea here. Okay, you could also, if you wanted to, you could smush it from the right and the left, which would mean that this right or left would get smaller and this side would get longer. Okay, but the main idea is that it's just a squished circle. You're essentially just smushing it down from opposite sides, and one side's getting longer and the other side's getting shorter. This also results in differences in their parametric equations and rectangular equations, in all honesty. But looking at the parametric equations here, okay, what do you notice they have in common? And what do you notice that's different? So take a quick look at these guys here. Okay. So hopefully you notice that what they have in common here is that they both use cosine and sine. Okay, so they both have sine and cosine, and they both have h and k being used. They're centers. Okay, so they both have h and k being used, the center of the figure. And I'm hoping that you notice the differences here and here. Okay, the differences in the equations is that for our circle, both sine and cosine are being multiplied by the same number. Okay, whereas in an ellipse, cosine is being multiplied by a different number than what sine is being multiplied by. And we'll talk about where you get those numbers. Okay, so the number before the sine and the cosine functions is different for an ellipse, whereas it's the same for a circle. Okay. All right, so let's talk about then parametric equations for an ellipse. First, we want to talk about the rectangular equation for an ellipse. So given we have our center at HK, okay, given our center at HK, our ellipse is x minus h squared over a squared plus y minus k squared over b squared is equal to 1. Okay, now where do A and B come from a graph? Let's just quickly spend some time and understand. Okay, I hope you realized that this right here, the x minus h squared, the y minus k squared, that's straight from the circle equation. Okay, the only difference is now we have equal to 1, and that's because our radius isn't a perfect radius anymore. This isn't a perfect circle anymore. So the a and the b here are kind of the radius for each axis. So if we take a look at the x-axis here, right, the x minus h squared, this a represents the distance from our center to the point on the ellipse that is directly horizontal to it, directly to the right or to the left of it. So this distance from h to this point right here, this is a. And h to this point right here, this is also a. So this is your like horizontal radius, for lack of a better term. Okay, and then we have our b, which is under the y minus k, which means this is going to be on the vertical axis here. So the vertical axis here, again, from center to the point that's directly vertically above or below the center, the distance from that center to that point is b. Center to that point is b. So that distance right there is b. Okay, so it's the b here would be the radius of our vertical axis. Okay, now depending on how your ellipse is smushed, right, the longer axis is always called the major axis, the shorter axis is always called the minor axis, but that's not important for us. What we want to pay attention to is that the a is our horizontal distance from center to a point, b is our vertical distance from a center to a point. So then when we write our parametric equations for the ellipse, what ends up happening is we take the h and the a from our x equations here. So x minus h squared over a squared, we take the h from the center and the a from the denominator, and this becomes h plus a cosine of t. So we're multiplying by that horizontal radius, for lack of a better term, and then we add or subtract our h from our center, the x value from our center. Similarly for the y, it all comes from this fraction here, y minus k squared over b squared. So we have y is equal to now our k, the y of our center, plus b, the vertical radius, sine of t. Okay, so let's take a look here. Let's do an example real quick. All right, so we're given our rectangular elliptical equation, x squared over 9 plus y minus 7 squared over 10 is equal to what? The first thing we want to do is we're going to need h, k, a, and b. So we can easily pull out the center here. I just have an x squared, which means my h is going to be 0. And then I have a y minus 7 squared. The minus from here, the minus here is the minus in the equation. So that means my k is really just a positive 7. Okay, so that if you have a minus in your actual formula, that means it's going to lie to you no matter what. Okay, so C, our center is at 0, 7. H is 0, K is 7. Then we have to figure out A and B. But notice that the denominator here, this is A squared and B squared, which means this 9 represents A squared, this 10 represents B squared. So we actually need to go ahead and solve for the real A and the real B. So we take A squared and we set it equal to 9. We square root and we get A is equal to 3. Okay, so we have our H and our A, and we can write our X parametric equation here. We know that H is 0 plus 3 cosine of t. So 0 plus 3 cosine of t, which simplifies just to 3 cosine of t, because 0 plus 3 cosine of t is just 3 cosine of t. So that's our X parametric equation. Now we solve for our b for the y. So b squared is equal to 10 square root. B is equal to the square root of 10. If you really want to, you can actually estimate that to the 4th decimal place. So 3.1623, but the most accurate representation of b is square root of 10. So we take our k, which is 7, and then our b, which is the square root of 10, and we get that y is equal to 7 plus the square root of 10 sine of t. Okay. Now the beauty is here, if I were to go ahead and figure out my center here, so I have 0 and 7, so 7 is right here, so that would be my center. Oop, my bad. That would be my center right there, right? I can go 3 to the right and 3 to the left and get my point here. So I have 1, 2, 3. I have 1, 2, 3. So that's my horizontal radius, 3. That's A. And then my B is 3.1623. Notice how they're really, really close, right? But they're not exactly the same, which makes this an ellipse. So if I go back to my center now, B is my vertical radius. So I can go 1, 2, 3. And then here's that little 0.1623. Going back to my center, 1, 2, 3, and here's my little 0.1623 right there. Okay, so that's what makes this an ellipse, the fact that it's not a perfect exact radius all around, right? It's a little bit longer on the vertical end. Okay, let's try another one. I want you guys to actually try this one out. Do as much as you can, see what you can answer in the questions that pop up real quick, and then we'll go over this together. Okay, so first we want to identify our center, and hopefully you got that this x minus 3 means that h is a positive 3, and that y plus 2 means that k is a negative 2. And again, that means we had a y minus a negative 2 here, right? So this plus came from the fact that it was minus a negative. This minus, and then the negative from the 2. Okay, so that means our k is a negative 2. And then if we go ahead and we solve for our a and our b, okay, a squared is equal to 25, square root a is equal to 5. Okay, which gives me my h and my a for my x equation. H is 3, a is 5, so we'll have x is equal to 3 plus 5 cosine of t. Make sure you plug things in the correct spots. Okay, we add h, we multiply the a. And then we go through with the b, and we have the square root of 4, which makes b 2. And then we have that our k is negative 2. So that means we're going to have negative 2 plus 2 sine of t. Okay, so we'll have 2 from the b, the negative 2 from the k itself. Okay, and again, these are our radii, right? Our horizontal and our vertical. So if we go to the center of this circle here, center of this ellipse, we have 3, negative 2. So 3, negative 2 is right here. Okay, so 3, negative 2, that means if a is 5, then that means I have a horizontal radius or distance of 5. So I can go 1, 2, 3, 4, 5. It gives me that point. Go back to the center. 1, 2, 3, 4, 5. That's my horizontal. My vertical, distance of 2 from the center to a point. So back here I have 1, 2, up, I end up at that point. Center here, 1, 2, I end up at my bottom point. Okay, so very simple here. Center, and then you can even use your horizontal and your vertical radii to get your points, and then connect your curve if you needed to graph this. Okay, so writing the rectangular equations now. Okay, we have x minus 2 cosine of t minus 3 and y equals 5 sine of t plus 4. First thing you want to do is you want to pull, okay, your center out. So your h and your k, you have negative 3 and 4. Okay, and then you have your a is equal to 2 from the cosine. Square that because you're going to need the squared version. So a squared equals 4. And then you're going to need your b